Right. So we are moving on to question number 6. Right. So the first part is explain why the rate of a reaction increases when the concentration of the reactants are increased. So in chemical kinetics, the first thing is to identify the factors affecting the rate of the reaction. So this part A is based on that, right? So why the rate increases when the concentration of the reactant is increasing? You have to mention when the concentration of the reactant is increased, the amount of the moles of reactants per unit volume is increased, so that the number of collation increases, which gives the idea collation rate is increased, and the properly oriented collations increase so that the rate is increased. Okay, so these factors are very important. In the marking scheme, they have not expected the collation rate, but they have also not expected the properly oriented collation. But in your scheme, when you are writing, please write down the properly oriented collation, because not all collation going to make the products, only the properly oriented ones. So this is why it is increasing. And explain reasons to explain why in general the rate of reaction increases with temperature. So we have discussed this before. The temperature effect can be explained in two ways. One is the collation rate, the other one is according to the Boltzmann distribution. So they are asking these two. So what you have to explain is increasing temperature, increasing kinetic energy of the molecules, so increasing collation, so increasing the collation rate, increasing the properly oriented collation rates, therefore rate increases. That is one part. The other thing is, according to Boltzmann distribution, you can tell at higher temperatures there is more number of the fraction of molecules higher than the activation energy is higher at higher temperature, therefore rate of the reaction increases. Okay, so those are the two factors. And question number 3, what is the relationship between the order and molecularity of an elementary reaction? So in the theory class, I explained to you there are two types of reaction. One is elementary reaction with a single step, more or less, and the multi-step reaction. So for elementary reaction, I told you the order is same as the molecularity. So what is the relationship between order and molecularity? It is same. Order equals molecularity. But for multi-step reaction, please remember you have to find the order with respect to each reactant separately by experimental conditions. So that is very important to understand, right? Question number 4. Sketch the structure of the activated complex of the elementary reaction NO plus O2, NO2 plus O. So this question, a similar, very same question have been already asked in 2011. Okay, because I explained this to the students in my theory class, because this is already asked. And we use this example, the question of 2000, as an example to explain the bond breaking and bond forming, right? So you have to draw the activated structure, right? Structure of the activated complex. So normally this is an elementary reaction, so it is goes through like this. We don't know either it is endothermic or exothermic, so I will draw like this. So the reactants are NO plus O2, and the products NO2 plus O. So the activated complex, so this structure. So remember, this reaction to happen, the collation should be properly oriented. For an example, you have this NO, okay, that is going to collide with oxygen like this. Okay, so if you think this collation happens like this and give us the products, this is wrong, right? Because NO2 is formed. Here NO2 is difficult to form, right? So the correct orientation would be NO reacting with oxygen like this, right? This is the collation. Because now this oxygen can be transferred to this NO forming NO2, and this atomic oxygen is formed. right? So what is the activated complex structure? Remember, in the activated structure, when you are drawing the activated structure, the bonds that are broken and the bonds that are formed, you cannot express that using a solid line. You should express that as a dotted line, right? So when this reaction happens, there is a bond formed between nitrogen and oxygen, and these two bonds are going to be broken. So basically, this is dotted. This oxygen is here, and this is which the bond is formed is dotted as well. So you can show here as bond formation, and this one bond breaking. Okay, so this is the activated structure, right? So this is the activated structure. You have to draw. This is done. And if you want to check this question, you also can check 2011. So it is after about 18 years, they have again asked about this question. Write the rate expression for the elementary reactions. This is also an elementary reaction that is given XA plus YB going to give ZC, where the rate constant K is K and the stoichiometry is XYZ. So typically you can write down in the elementary reaction, the order is equal to its molecularity. So R is equal to rate constant K times concentration of A to the power X and concentration of B to the power Y. So this is the rate expression, right? That is done. Now moving on to part B. So part A is directly connected to part B. So we will quickly go through this, right? So what is the condition? The reaction XAYB was studied in a two-phase system consist of an organic solvent and water. So think about this. This reaction that is asked in the final question of part A is studied in a two-phase system. Normally in chemical kinetic, we try to study the reactions in a either aqueous phase for aqueous reactants or organic phase for organic reactants, right? So we don't know what is this aqueous and organic here, these reactants A and B. So therefore they have studied this in a two-phase system, organic solvent and water. So that is nice. The compound A is soluble in both phases, while the compound B, C are soluble only in aqueous phase. So this gives you the idea. A, since it is soluble in both phases, this is going to be like this. A should be distributed both in the aqueous phase as well as in the organic phase, right? Because so in the system, right, A should be in the aqueous phase and should be distributed in the organic phase according to its KD expression, right? There should be a KD value because there is an equilibrium here at constant temperature. And here, if there is a B, like this reaction C is happening, and these all are only dissolving in the aqueous phase, and there is no connection for organic phase, right? So we will discuss what they have asked here. The partition coefficient for the distribution of A between phases. So they have given this, so that is very nice. So KD was equal to 4.0, and it is concentration of A in organic phase, okay, over concentration of A in aqueous phase. So that is nice. This KD is given, right? The compound A was added to two-phase system and allowed to reach equilibrium. So what they have done, they have first initially added A and shaken and kept for the layer separation. Then A is there. Then what they have done? The reaction was started by injecting the compound B to the aqueous phase. Now, how they have entered B. So they have injected here. So this is an injection. Okay, this is injected. So injected B. So initially, after the equilibrium, there is only A. It doesn't mean that reaction is happening. When the injection is done by inserting B, then this reaction starts. Okay, so that is the idea. The temperature of the system was maintained at a constant value and the results of the experiment is given. So initially we have A, and when I inject B, then this reaction happens, right? So they have studied several reactions. In fact, 3 experiments, and the volumes and all those things are given, right? So we will try to draw these 3 steps here. So for the first one, there is only the aqueous phase, right? And it is 100 cubic centimeter. And you have 1 into 10 to the power minus 2 moles of A. One into 10 to the power minus 2 moles of B. This is experiment 1. Experiment 2, again, okay, now they have the organic. 100 cubic centimeter of the organic, 100 cubic centimeter of the aqueous. Okay, so here there is organic and aqueous, but here there is only aqueous, and A added is 1.25 into 10 to the power minus 1 of A. B was 1 into 10 to the power minus 2 moles. B is not changed there. This is experiment 2. And experiment 3, I will show you the screen after drawing all these things. They have used 50 cubic centimeter of this and 50 cubic centimeter of this. So aqueous and organic. And here they have used 6.25 into 10 to the power minus 2 moles of A. And 1 into 10 to the power minus 2 moles of B. So these are the all information that is given. And in fact, other than this, what they have given, at this particular condition, when B is injected, the initial rate is given here as 1.2 10 to the power minus 5 MOLDM minus 3 per second. In the second experiment, the rate is given as 7.5 10 to the power minus 5. And the third step rate is given as 1.5 into 10 to the power minus 5 to 3 minus 3 mole DM minus 3 per second. All these, huh? Right. So calculate the initial concentration of A in aqueous phase in experiment 1, 2, 3, and all. So 1, 2, and 3. So what is the initial concentration here? So initial concentration is they add 10 to the power minus 2 moles of A. So A will be equilibrating like this. Then when you inject B, this reaction is going to happen. So initial concentration of A is after the equilibrium. But the problem here is you don't have any organic layer for the equilibration. So there is no problem for this finding the concentration of A, right? Because A will be just in the aqueous phase, and there will be B, and this reaction will give you C. So the initial concentration of A will be the initial concentration as you added. So concentration of A will be, concentration initial of A will be 10 to the power minus 2 moles divided by 100 into 10 to the power minus 3 decimeter. So you can easily find that, right? 10 to the power minus 2, 100 into 10 to the power minus 3. So it is 10 to the power minus 3. So I want to write everything, then it will be easy for me, right? So the initial concentration here is this is -2. So it will be -2 divided by 100 into 10 to the power -3. So here there is a -1. So this will be coming up. So 0.1. This is 0.1 newton. Okay. But what about here? Here it is different, because now since there is an organic, A will be distributed like this, right? So you don't know the amount of A present here after the equilibrium, right? So what you have to do here, you get the amount of A in organic phase at equilibrium. After equilibrium, you get this as X. And here, this amount after equilibrium in the aqueous phase will be the initial mole minus the amount that is went to the organic phase. So this will be 1.25 minus 6. 1.25 into 10 to the power -2 minus 6. Okay. So if you know these two, and if you know this KD value, you can plug here, and this one will be X over the volume is 100. And here this one will be 1.25 into 10 to the power -2 minus X over 100 into 10 to the power -2. So these two will be cancelling out. So you will have an equation for E is equal to X over 1.25 10 to the power -2 minus 6. Okay. So you can find the value of X, subtract X from 1.25 into 10 to the power -2. Then you will have the initial amount of A present in this aqueous solution, and then you can find the concentration of it. Okay. So when you do these steps and find the concentration of step 2, so I will tell that. Where is it? I have to find. Okay. So it is 0.25. Okay, so the initial concentration here is 0.25. Okay, so in the same way, what you can do here, is you can do this. You can get the amount that is going to the organic phase as Y, and this will be then 6.25 into 10 to the power -2 minus Y, and you can find Y, and you can find the initial concentration of A as well here. Okay, so when you find the initial concentration of A here, and it will be again 0.25. 0.25. So you have to understand, in the first experiment, my initial concentration of A is 0.1. In the second, it is 0.25. In the third, it is still 0.25, although the volume is reduced, but I have used different amount of A. That is why the concentration is same when the volume is changed, right? So we can do that question. The first part of that question. Then we will discuss the second part. Okay. So we have found the initial concentration, and then they say find the order of the reaction with respect to A. So this is very simple. Why? Because you have to understand here, in this one and this one and this one, in all three experiments, if you want to find the order with respect to A, you have to find two reactions where different concentrations of A have been used and same concentration of B have been used. So when you think about this one and this one, the concentration of A is different. But check the concentration of B. This is 1 into 10 to the power -2 moles in 100 cubic centimeter. And here also 1 into 10 to the power -2 moles in 100 cubic centimeter. So according to our rate expression, if you can remember, R is equal to K times concentration of AX BY. So rate for this expression is given 1.2 into 10 to the power 5, rate constant. Concentration initial 0.1 N times X. B concentration is 10 to the power -2, 100 into 10 to the power -3. So again, it will be 0.1. So this will be 0.1 y. So this is for first. And for the second, the rate is given as 7.5 into 10 to the power minus 5. These are minus values. And now this is 0.25 into x. And concentration of B still remains the same because 1.1 into 10 to the power minus 2 in 150. So this is second equation, right? So when you divide these two, this one will be cancelling. So y is not there. So only the calculation will remain with x. And when you solve this one, so basically this is 100 over 25, it is 4. And this ratio is going to give 1 over 4. So the x, what you can do is, the simplest way to do this is you take this as 10 over 25. So it will be like 100 over 250, which is typically 1 over 4. Then you can get this expression. So basically it will be 1.2, 7.5, and here this will be 2 over 5 to the power x. Okay. So you divide this and see the ratio, and based on that you can calculate x. And when you do the calculation, you have to get x is equal to 2. Okay, that calculation is not hard. You just have to divide and see. Okay, that is what I am confused. This is 6.25. The rate. There is. Give me a second. Yeah, 7.5. This is 7.5. This is 7.5 divided by 1.2 is 2.5. So this is the reverse is 2.5. So typically it is 1 over 2.5 times 1 over 2.5 x to the power 2. So basically this is x is equal to 2. Okay. 7.5 when you divide by 1.2, it is 6 point something, and 5 over 2 is 2 point something. So 2 point something squared gives you 6 point something. That is the idea, right? That is the overall idea. So I want to mention this: finding x is not difficult. The other thing that I have to mention here is, check this. So you find A, then you find B. So this is the point where many students get upset, right? Because to find B here, I can use these two, experiment 2 and 3. Because for A, it was easy for find A 1 and 2 because concentration of A is different, concentration of B is same, 0.1, 0.1. Then to find B, you can go with this one and this one. So we have the rate expression, R is 1.5 into 10 to the power minus 3. Concentration initially is 0.25, and concentration of B here initially is 1.2 divided by 50 into 10 to the power minus 3. Okay, and for this reaction rate is 7.5 into 10 to the power minus 5. Concentration initial of A is 0.25 to the power 2, because now we know the order, so we don't have to worry about that because concentrations are equal. And the concentration of B is 1 into 10 to the power minus 2 divided by 100 into 10 to the power minus 3, which is 0.1. We have already calculated that. And when you divide these two, you can find the order with respect to B, which is Y here. The point that I wanted to emphasize still here is, when you do the calculation for B, normally here we end up with a whole number that will give us to solve further and find and get a good solution. Okay, but when you do this second part calculation, you will realize there is a problem. Okay, because the solution will not give a proper whole numbered answer. Because when you find Y, by using logarithmic table. That's very important because since you cannot solve properly, you have to use the log table. And when you find log, you will see y will be 4.34. This is the normal answer that we get for this particular second step question. And this y, you have to take that as 4. This is the point that I have to mention. Okay, because students got confused because normally in past papers we get proper solutions for x and y, the orders. We don't get as fraction values, decimal values, all those things. But this is the first time after a long period of time we get this question, this type of question where you find y, it is a decimal value. And since this is lower than 0.5, so here this is 0.34, so we can get y as 4. So there is no problem here. Okay, so student got confused because when they solve, they get 4.34. So they think we normally don't get this type of answers, so my calculation is wrong somewhere. But in fact, it is correct. There is no problem here. The only point is you have to take this order of y as y is equal to 4. Okay, so we found A, so the order with respect to A is 2, for B is 4. So rate constant, so since you know the order, so you can take one of these reactions and write down the order with respect to A as 2, B as 4, and the concentration included, and you can find the rate constant, either 1, 2, or 3 reaction. Okay. In another experiment, in the experiment 3 above, after adding A, okay, allowing the system to reach equilibrium, if a 10 cubic centimeter volume was removed from the organic phase, what can be stated about the initial rate of the reaction giving results? The idea is, so experiment 3 is this, right? So you had A in the aqueous, A in the organic, and this equilibrium is established, and then you inject B, and this reaction produces C, right? What they are mentioning here is they remove some amount of organic phase, okay? Some amount, 10 cubic centimeter, in fact, is removed. And they ask whether something is happened here in the A, okay? The idea is this: when you remove this, a new equilibrium is established, right? But the thing is, for the rate, only the initial concentration is affected, and the concentration of A in the aqueous phase is not going to change. Some amount of A is going out, but the concentration of A is not going to change. Okay, so that is the idea. Because equilibrium is established, this entire 10 cubic centimeter is removed. It's like for titration, you remove this one. Nothing is happened here in the equilibrium system. The concentration here is not going to change. Okay, because this is after reaching the equilibrium. If before reaching the equilibrium, then there is a re-establishment of the equilibrium and a new concentration is formed. But after reaching equilibrium, the equilibrium is already reached. The concentration terms have become constant. Okay, the concentration of A depends upon the rate here, so it is not changed. So the initial rate is not going to change. That's the idea, right? Okay, the last part. The mixture of liquid X and Y behaves ideally. Okay, very nice. At constant temperature, when the liquid phase in equilibrium with the vapor phase in a low closed rigid vessel contain 1.2 moles of X. And okay, so when the liquid phase is in equilibrium with the vapor phase in a closed rigid vessel, okay, this contains 1.2 moles of X and 2.8 moles of Y. The total vapor pressure is given, okay. At the same temperature, when the composition of liquid phase is changed to 1.2 moles of X and 4.8 moles of Y, the total vapor pressure is, okay, so this is typical soluble, it's like a little bit of difficult, but it is not much difficult than your O-levels, right? Because they have given two different systems, right? So in the first one, they have given the total pressure, that is 3.4. So you know this total pressure should be come from Px plus Py, right? Because they are asking the saturated vapor pressures. So we have to use Raoult's law. So for Px, I can write this as P naught x. That is what the Raoult's law says. Raoult's law says P naught x times mole fraction in the liquid phase. So you can find the mole fraction of the liquid phase in the first experiment, right? Because 1.2 moles of X and 2.8 moles of Y. So X mole fraction will be 1.2 divided by 1.2 plus 2.8. So this is Px plus Py will be P naught Y times 2.8 mole fraction over 1.2 plus 2.8, and this will be Py, and this total pressure is given as 3.4 into 10 to the power 4. So this is system 1 and this is our equation 1. Okay. In the second case, they are telling you have 1.2 moles of X. So it is same. So this will be P naught X, 1.2 moles of X, but the mole fraction will be now different because Y amount is different, 1.2 and 4.8, right? Plus P naught Y is 4.8 now over 1.2 plus 4.8. So these are not hard questions. So the total pressure is 3.6 to the power 4 Pascal. So this is equation number 2. So this is 1.2 over 4, 2.8 over 4, 1.2 over 6, 4.8 over 6. So this, what type of a question is this? So only thing that you don't know here is P naught X and P naught Y, and you have two different equations to solve. So this is now your duty. Now this is all else, right? So this is these are two simultaneous equations, right? So you have to just solve the simultaneous equation and get the values of P naught X and P naught Y. Okay, so this is a very small question. You can see the same question in the following 2018-19 papers as well, one of the papers. Okay, so these two are now O levels. So if you can't do this, you have to go to O levels like SRD, row circles. Okay, so this is a nice question that you need to understand, where kinetics is combined to what? Phase equilibrium, homogeneous, part B. And second is heterogeneous phase equilibrium, and it's a new different question that is asked.